Today we're talking about measurements, matter, and dimensional analysis. When we take a measurement, we are provided with three types of information. We're given the size or magnitude of the measurement. We're given the standard of comparison for the measurement or the unit. And it's really important to always include your units when taking measurements. Even whenever you're doing calculations with your measurements, make sure that you have them. You're also given an indication of the uncertainty of the measurement. For example, if we have a ruler here, we have all these marks. We have 5, 2, 3, 4, 5, and 10 right here. Say you're measuring something and it lines up right here. And you put it up and you say, well, it comes right here. That will be 5, 6, 7, 8. This right here would be 9. This would be 11 because I didn't quite draw it in correctly. So let me correct this. So that'd be 1, 2, 3. Oh, this is correct. 4, 5. So this is 10. So this is 5, 6, 7, 8. It's not quite 9, but it's not 5 either. So this is where the uncertainty comes in. So you know it's 5 point, or not 5 point, 8 point something, because it comes up right here. So if I'm looking at that, I have to estimate. I'd say about here is half, and it's halfway in between the half and the next number. So I would say it's about 5.7. Now this number right here is an estimation. So I'm only certain up to this number. I know that it's at least 8. I know that it's 8 point something. That's with certainty. But this last number, I had to estimate what it was. So that gives you an indication of the uncertainty of the measurement. This estimate is the uncertain number. Now, whenever we are writing these long numbers, because sometimes measurements can be really, really long, especially if you're in the trillions or quadrillions, you have a lot of zeros. And we can get confused or forget how many zeros we're supposed to have. And so writing things into scientific notation actually helps us keep track of the numbers better and helps us manage them better. For example, we're given 298,000 kilograms here. We want to turn it into scientific notation. So how do we do that? Well, we find the decimal. If there's no decimal, we know at the end of the number, there's a decimal there. If we wanted to make it bigger, we had to put a 0.000 whatever. So the decimal always comes at the end of the whole number initially. So we look, and I want to turn it into scientific notation. So I move the decimal place over until only one digit is in front of the decimal. So to do that, I go 1, 2, 3, 4, 5. So my decimal would go in between my 2 and my 9. So right here it is. And since I moved it over 1, 2, 3, 4, 5 places, it's now times 10 to the 5th. That positive 5 indicates that we moved the decimal to the left, which means we're going to have to add zeros behind to make it the number that it is. So we're going to have to move this over to the right to make it large again. So if we had 2.98, times 10 to the fifth, we'd say 1, 2, 3, 4, 5. My decimal place goes at the end. I fill in the extra with zeros, and now I have 298,000. Let's look at the next example. We had 0.00000025 kilograms. Let's turn it into scientific notation. My decimal is already way out in front, but I need only one digit in front of the decimal. So I move it over 1, 2, 3, 4, 5, 6 spots. So now my decimal is in between my 2 and my 5. And because I moved it to the right 6 times, it's negative. So anytime you see a negative, that means you have a decimal here. Let's look at this one. What is 0.00036 in scientific notation? I'm going to move it over 1, 2, 3, 4. So if I move it over 4, it's 3.6 times 10. Is it going to be negative or positive 4? Which direction did you move it? We moved it to the right, the decimal to the right. If we move it to the right, it's negative. So it becomes 3.6 times 10 to the negative fourth. Say we have 5.31 times 10 to the negative third. How is that in your expanded form? What is this if we want to put it in its full notation? We're going to say 1, 2, 3. Fill in those extra spaces with zeros. So then it becomes 0.00531. If you need extra help, please let me know so that we can get you some more practice and understanding. Now, measurements always contain a unit. We have the SI system, which is what the scientific community internationally uses. For length, it's meters. Here's your symbol. Mass, kilograms. Here, time, second. Temperature, Kelvin. Current, amount of substance, and luminous intensity. We're not going to use amperes or candelas in chemistry, but if you take physics, you'll see it there. Now, you'll notice that some are lowercase and some are capital. It's actually really important to keep what's lowercase, lowercase, and capital, capital. Otherwise, you're going to indicate something else. For example, a capital M in chemistry means something completely different than meter. So, which is your lowercase m. So make sure you're diligent in keeping what's supposed to be capitalized, capitalized, and what's supposed to be lowercase, lowercase. We don't measure everything in strictly meters. We have some really small things and we have some larger things. So that meters is our base measurement unit. Excuse me. But we can have centimeters. If we add a C in front of the M, it's centimeter. So a centimeter is 1/100th of a meter. It's 10 to the negative second. We have decimeters. We have kilometers that we use for large distances. Here in the US, we see mile markers and we say go a mile this way or that way. In the rest of the world, they use kilometers. And you judge distance on that. You also have gigabytes, terabytes, and megabytes that I'm sure you've heard of with your electronic devices. And you can see those sizes. A terabyte is 1,000,000,000 times 1 byte. A gigabyte is 1 billion times 1 byte. So you can see the massive amount of storage that your devices have using those prefixes. Now, a standard unit of length in the SI and metric system is the meter, as I talked about on the previous slide. A meter is actually the distance light travels in a vacuum in 1,299,792,458 of a second, which is quite a large distance in 1 second if you add all those pieces up. So you can imagine how quickly light travels. Here you can see that 1 inch equals 2.54 centimeters. I've used that in converting lengths more often than I could tell you. Quite frequently, even now, I still use that measurement conversion. So standard unit of mass in SI systems is the kilogram. If we have 1 liter of pure water, you have 1 kilogram in mass, which is the equivalent of 2.2 pounds. There are things called intensive properties. You have intensive properties and extensive properties. Intensive properties don't depend on the amount of matter in an object. The properties are there regardless. The extensive properties depend on the amount of matter in an object. So intensive properties such as temperature, time, and volume don't depend on the amount of matter in an object. So temperature, the SI unit is Kelvin, which is a capital K. And degrees Celsius is sometimes used depending on the equation and the relationship that you're looking at. But sometimes it's necessary to convert kelvins into degrees Celsius or degrees Celsius into kelvins. So say we have something at 25 degrees Celsius. That's basically room temperature. And we want to find out how many kelvins it is. All you're going to do is add 273. So 25 degrees Celsius plus 273 equals 298 Kelvin. If you have something at 0 degrees Celsius, which is freezing, you just add 273, and you know that freezing here on Earth at 0 degrees Celsius, that's the temperature that water freezes. You add 273, you get 273 Kelvin. So 273 Kelvin is the freezing point of water. Time, the unit, SI unit is a second. And then volume, the cubic meter is the SI unit. Sometimes we use centimeters, of course, so a cubic centimeter is the equivalent of 1 milliliter. And in medicine, they'll actually use that. And if you've ever heard of cc's, like you've been in a hospital setting or you're watching a medical show and they say, give him 10 cc's, all they're saying is give him 10 cubic centimeters, which is the same as 1 milliliter. Here we have density, and you will be doing these calculations. So density equals mass over volume. Remember, M lowercase stands for mass, and V stands for volume. If you put those together, it kind of looks like a heart. So I'm trying to help you remember what the formula is. So density is mass over volume. That looks like a heart. And if you know the old 80s song, shot to the heart and you're to blame. You give love a bad name. So density is basically mass over volume, which is a shot to the heart. So if you can remember density and shot to the heart, you got the formula. Here are some common densities, and you can notice that solid ice is less dense than liquid water. Most solids are more dense than their liquids because of the hydrogen bonding, which we'll talk about later this semester. Ice can float, and life is very happy because of that. Otherwise, we wouldn't exist. Okay, let's do a practice problem. This one's a little tricky. Gold in bricks, bars, and coins has been a form of currency for centuries. In order to swindle people into paying for a brick of gold without actually investing in a brick of gold, people have considered filling the centers of hollow gold bricks with lead to fool buyers into thinking that the entire brick is gold. It doesn't work because lead is a dense substance, but its density is not as great as that of gold, which has a density of 9.3 grams per cubic centimeter. So, what is the density? So, what are we looking for? What is the density of lead if a cube of lead has an edge length of 2.00 centimeters cubed? I like to write everything down as I see and identify it because otherwise I tend to get overwhelmed. It's a lot of words with some numbers in there, so I need to break it down. This here, this is all filler. Just a little history lesson because people did do this. What is the density? So that tells me I'm looking for density of lead. If a cube of lead has an edge length, so a length of 2.00 centimeters cubed, and a mass of 90.7 grams. So I need to find the density. Well, what do we know that the density is? Well, we know density is, if we remember our song, mass over volume. Remember, it's our heart with a shot to the heart, and you're to blame. You give love a bad name. And you just try to remember that. I remember I create little things to help me remember. That one is perfect. Okay, so we have our mass right here. We want to find our density, but we don't have a volume. Well, if you remember from your other classes that you've had in math, volume is length times width times height. This right here is a cube. And that's what it's telling us. It says it's a cube. So visualize a cube. The cube has a length of 2 centimeters. What do we know about cubes? Right, that its width and length and height are all equal. So this is going to be 2.0 centimeters, and this is going to be 2.00 centimeters. I do have to apologize for my writing. So my volume then is going to be 2.00 centimeters times 2.00 centimeters times 2.00 centimeters, which equals 8.00 centimeters cubed. So now we have our volume, we have our mass. Now we can solve for density. So our density is our mass, which is right here, 90.7 grams over our volume, which is 8.00 centimeters cubed. So if I put that into a calculator, that is 11.3 grams per cubic centimeter. Remember to always include your units. If you remember that density is always grams per cubic centimeter, and you put in volume over mass, you know that you are doing it incorrectly. So knowing your units and what you're looking for can help you solve the problem correctly. Let's look at this next problem. This one is just about volume. So, to 3 decimal places, what is the volume of a cube with an edge length of 0.843 centimeters? I want you to take a moment to pause and try these on your own, and then come back and see if you did it correctly. So just push pause, work on them, do your best, and then check. Push play and check your answers as we work through them together. So to 3 decimal places, what is the volume of a cube with an edge length of 0.843 centimeters? We know volume is length times width times height. So the volume is going to be 0.843 centimeters because we're working with a cube times 0.843 centimeters times 0.843 centimeters. So that's going to equal, let's put it in our calculator, 0.843 times 0.843 times 0.843. This gives us 0.599 cubic centimeters. Now, if the cube in part A is copper and has a mass of 5.34 grams, I'm going to write the number I'm given and identify what it is. So it said mass, and I knew that was M, 5.34 grams. So I have simplified that. What is the density of copper to 2 decimal places? So what's the density? To know what density is, we have to remember the formula, and you're going to get tired of the song at this point. Remember, draw your heart and draw your arrow. Shout to the heart, and you're to blame. You're going to be blaming me, I'm sure, by the time this is done for having that stuck in your head. So now we can calculate our density. We have our mass and we have our volume from part 1 here. So now we can see our density equals our mass, which is 5.34 grams over 0.599 cubic centimeters. So again, in our calculator, a scientific calculator is something that you'll need. If you don't have a scientific calculator, please get one, or on your computer, let me do this, I can show you. There is Desmos right here. It's a scientific calculator. You can have it in different functions. You're able to put in your parentheses in sine, cosine, tangents. If you need one, please use that until you aren't able, until you're able to purchase one. So 5.34 divided by 0.599 gives us 8 point, oh, that's not coming up when I try. 8.91, because it asks for 2 decimals, grams per cubic centimeter. All right. Hopefully y'all did okay. And if you have questions about it, please reach out to me so I can help you. This next problem is another density problem. You can push pause and try it on your own. This one's a little different. So if you want to push pause after I show you how to find the volume to begin with, and then try it on your own, you can do that. So we have a man and he bought a golden figurine at a shop. He wants to know if it could actually be gold, because this is what happens. Archaeologists find something that's gold in color. They don't want to destroy it, but they want to determine what material it's made out of. And each element has a specific density. So you could find the density and then determine what the object is made out of. So this man got a golden figurine. He wants to know if it could be gold. And he measures its mass and finds it to be 31.48. So I'm going to put this down because it says its mass, 31.48 grams. Now he takes a beaker. So I'm going to draw this beaker. And he fills it with water. There's your water. To 25 mils. So I'm just drawing that picture for you. And it's a good thing. Write down what you need. Don't worry about wasting paper or someone thinking you're silly. Write it down if you need that visual. I need the visual, so I draw pictures. And you can see that I write everything down. It helps me organize. Now he places the figurine in the beaker and the volume rises to 29.0 milliliters. So here he has the beaker. He puts the figurine in. I'm making a little snowman. And it rises to 29 milliliters. Now, one thing to know is if it rises that much, and you know you have 25 milliliters of water, you can figure out what the volume of this figurine is. So the volume would be the 29 milliliters minus the 25.0 milliliters. And that gives you 4.0 milliliters. So now you have your mass, you have your volume. What is your formula? Remember, density equals, draw your heart, draw your arrow, shooting the heart. Play the song in your head. So density equals your mass, just 31.48 grams, divided by 4.0 milliliters. So if I do that in my calculator, 31.48 grams divided by 4 equals 7.87 grams per mil. The question didn't ask me for the density of the object. It asked me, is this object gold? So the answer is no, it's not gold. Now we could take this and look up what object or what material has this density and determine what the object is actually made out of. But if the man thought he got a deal on a gold figurine, it's actually not gold. So let's talk about matter. Matter is anything that has mass and takes up space. Mass is a measure of the amount of matter an object has. That was something we discussed in the last class. Weight, though, is a measurement of the amount of gravity on an object. So mass and weight differ. Weight is the amount of gravity, the measure of the amount of gravity on an object. You will have the same mass on Mars, on Earth, and on the moon, but your weight will be different in each place because of the amount of gravity differing. So mass is constant. Weight depends on gravity. We know that there are 3 states of matter: solid, fixed volume, and shape. Liquids, no fixed shape, but you do have a fixed volume. And gases don't have a fixed shape or volume, and they are very dependent on temperature and pressure. And we know that physical changes occur as substances change states of matter. So a solid melting into liquid, or a liquid evaporating into a solid. Now, most substances are mixtures, which is a combination of 2 or more substances. We have 2 types of mixtures. We have a homogeneous mixture, also known as a solution, and these look the same throughout, like salt water or Kool-Aid. Solutions or homogeneous mixtures can be solid, they could be liquid, or they could be gas. So mixtures aren't always liquid. Heterogeneous mixtures can also be solid, liquid, or gas. And these are mixtures that we can see the different parts, like a chocolate chip cookie. You could see the chips in the cookie, so you could see those different parts. So let's take a moment to practice. Hit pause. See if you can tell me what type of mixture is the following, and then come back and see what the answer is and check your work. So what type of mixture is the following? Granite. You could see all the different parts. So this would be a heterogeneous. Orange juice. Orange juice, if it's been filtered, everything, this is going to be a homogeneous or a solution. Sugar water. You mix in the sugar, you let the glass sit. You can't see the sugar because it's all dissolved in the water. So this is a homogeneous. Air. The air around us, we can't see. It all looks the same. We can't see how much nitrogen or argon or oxygen is in it. So this air is also a homogeneous. Steel. This is a homogeneous mixture. We can't see the different elements in it. So see how you did. Let me know if you have questions about it. But we can actually separate mixtures. We can do this through a few different ways. We can filter it, and that'll separate water and sand, for example. Or you have coffee filters in the grocery store to get all the coffee grinds out of your beverage. You can manually separate mixtures, like Cinderella did with the lentils in the fireplace. She had to pick up the lentils from the ash. Whenever you buy lentils, you usually have little tiny rocks in there. You have to manually pick out the rocks whenever you make lentils. I've missed a couple and almost broke a tooth before. You can also use a process called distillation. And distillation uses boiling points to separate homogeneous mixtures. This is how crude petroleum into gasoline is, or oil or kerosene is used. We also use this to make distilled water because water will evaporate faster than the minerals below. So if you have a still here, there's a tube coming out, you have your mixture here, and the compound with the smallest, with the lowest boiling point will evaporate first and eventually make its way down the tube into another container, and it will be the pure form here. And then once that has all evaporated, then you can work on evaporating the next component in your mixture. You also have crystallization, and that uses solubility to separate mixtures. To use crystallization, you actually use a solvent in this mixture. A solvent is what is being dissolved, or what is doing the dissolving, and you evaporate it. And you heat the solution slowly and allow it to cool slowly. And when you do that, the least soluble will form a crystal first to be removed through filtration. So separating mixtures can take a lot of time. They usually do, but that's how we get a lot of our pure materials. Now, pure substances are either elements or compounds. Elements can't be broken down by chemical changes. These are what are found on your periodic table. They're the gold, silver, oxygen, nitrogen, etc. A compound is two or more elements. So this would be like your sodium chloride. That's a compound. Sodium by itself would be an element. Now, a chemical change happens through a chemical reaction, and it changes the substance from one thing to another. For example, if we have H2O, we can break it down into hydrogen and oxygen. You've done a chemical change. If something rusts, so you have steel and it rusts, that is a chemical change because the iron is reacting with oxygen in the air, creating a new substance. So it's changing the substance completely. A physical change just changes the appearance, but not the substance. If I cut my hair, that is a physical change. The hair's still hair, but it's not changed its properties. Now, there are 118 elements organized in the periodic table, and rows are called periods. Columns are called groups. So here you can see all the elements that we have, all the known elements. Here's a flow chart if you like a visual to help organize. We know that everything that takes up space and has mass is matter. radio waves, light, etc., aren't considered matter because they don't have mass. We can break matter down into a pure substance, like your compound or elements, or a mixture. Those have two or more pure substances that and retain their individual identities. If it's a pure substance, we determine if it's an element, like on the periodic table, or a compound, which is two or more elements combined together. If it's not a pure substance, then it's going to be a mixture. And then we have to determine if it's a homogeneous mixture or a heterogeneous mixture. If it's homogeneous, it looks the same throughout, it's uniform throughout. If it's heterogeneous, we can see the difference. I want you to pause this, try to answer, and then push play and come back and look at this. So determine if the following are a heterogeneous mixture, a homogeneous mixture, an element, or a compound. Steel. We actually did this, and we determined steel was a homogeneous mixture. Tea with leaves. If we can see the leaves floating around, then this is going to be a heterogeneous mixture. Table salt, sodium chloride. Well, if you look at the periodic table, is sodium there? Is chlorine there? Yes, so this would be a compound. Kool-Aid. Well, that's a mixture, but is it a homogeneous mixture or a heterogeneous mixture? We can't see the difference, so that's a homogeneous mixture. 24 karat gold. If gold is 24 karat, it is pure. There are no impurities in it. If there are no impurities and it's pure, gold is an element. Again, as always, if you do have questions, please let me know. We are on our last subject for this week, last topic, and we'll do practice problems, and then you guys can take your quiz. So dimensional analysis we use to convert between units. Say we have inches, but we need centimeters, for example. We're going to use dimensional analysis. I have given you the base units, SI units before, and a chart. So this is just a review. And then we have our derived units, like our area, volume, velocity, acceleration, density, our force, and our energy. So let's look at the conversion process. We convert things incidentally on a daily basis without even realizing it. Here's an example. If we have 6 quarters, how many dollars do you have? Most of you can do this in an instant and not even realize you're doing the conversion process. So again, we start with what we know. Always start with what you know. We know that 4 quarters is in a dollar. We know that we have 6 quarters. So we set it up and we say 6 quarters times $1 for every 4 quarters equals $1.50. We know that our quarters cancel out, and that's why we're left with dollars. So I pulled up that math problem so you could see it digitally, but sometimes we need to see things written out. So I'll write it here. So we have 6 quarters. We put a ratio here. This is our ratio. What we want always goes on top. We want dollars. So I'm going to put my dollars. What we want to get rid of and cancel out This is why units are really important. We put on the bottom. So quarters go on the bottom. We know that for every $1, we have 4 quarters. So this ratio comes from this that we know to be true. My quarters cancel out, so 6 times 1 divided by 4 gives me $1.50. Let's do another practice one. If we have 12 dimes, how many dollars do you have? Hey, let's think. We know that 10 dimes equals $1. We're starting with 12 dimes. Always start with what you know, which is 12 dimes. I know I can go from dimes to dollars. There's a direct conversion there. What do I want? I want dollars. I always put what I want on the top, what I want to get rid of on the bottom. And I know for every $1, I have 10 dimes. Dimes divided by itself, because it'd be dimes times dollars divided by dimes, would cancel itself out. So this is 12 times 1 divided by 10 equals $1.20. If you have questions, let me know. I don't want you to struggle with this. Practice is the best way to understand the process. Reach out to me if you have questions. I am happy to schedule time to work. So length, we have some conversion factors, mass and volume. Here are some more common conversion factors. You have these in the guided notes as well, so those should help. So let's look at these. Push pause and try these on your own. And then whenever you're ready, come back and we'll work through them. So how many inches? So we're looking for inches. I'm writing down we want inches in 3.5 feet. Okay. Well, what's the conversion between feet and inches? On the previous slides, we know that there are 12 inches and 1 foot. Okay, so I start with what I know, or what I'm given. I'm given 3.5 feet. And I set up the conversion factor. I can go from feet to inches because I know there are 12 inches for every foot. What do I want? I want inches. So inches is going to go on top. What do I want to get rid of? Feet. So it goes on bottom. Now I put in for my ratio. I know that there are 12 inches in every foot. My feet will cancel. So that's 3.5 times 12 divided by 1, and this gives me 42 inches. Let's try another one. We have the density of ethanol at 20 degrees Celsius is 0.7893 grams per milliliter. And this is density, so I'm going to write this down. So density equals 0.7893 grams per mil. What's the mass? So it says what is a mass? So I'm looking for mass of 10 mil of ethanol. So 10 milliliters is volume. What is our equation for density? Remember, we have density equals our heart with our arrow shot through. So density equals mass over volume. We have our density here. Our density is 0.7893 grams per mil. And that's equal to our mass, which we don't know, all over our volume, which is 10.0 milliliters. Now we need to solve for our mass right here. So what do we do? Well, we need to get our milliliters off the bottom. So one way to do that is to multiply it by itself. Because this means you have mass times 10 divided by 10. Anything divided by itself cancels out. But you can't do something to one side of the equation without doing it to the other. When I was little, I couldn't scratch one side of myself without scratching the other. So if I scratched my right arm, I had to scratch my left arm at the same spot. Same thing here. Mass divided by volume times its volume cancels out, equals our volume times our density. Now, what happens with our milliliters? We have milliliters times grams divided by milliliters, so our milliliters are going to be canceled out. So now it's going to be 10 times 0.7893, so our mass is going to be 7.893 grams. It's a little bit different. All we're doing is rearranging. We're not just plugging it in anymore. Now we're having to rearrange it. Okay. Another practice question. How many kilograms is 150 pounds? Remember that 1 kilogram equals 2.2 pounds. Start with what we are given. Given 150 pounds. Okay, now we want to turn it into kilograms. We're looking for kilograms because it says how many kilograms. We always put what we want on top. We're looking for kilograms, so it goes on top. We put what we want to cancel out on bottom. We need pounds to cancel out. We'll put pounds down here. We know from this that 1 kilogram equals 2.2 pounds. My pounds will cancel out because I have one on top, one on bottom. So this is 150 times 1 divided by 2.2. So 150 pounds equals 68 kilograms. Okay, let's look at this next problem. It's another density problem. Here we have it. The density of gold is 19.30 grams per mil. Don't be afraid to write things down. It helps you keep track of things. It says, what is the volume? So that means I need to figure that out. Of 10.123 grams of gold. So we want to know the volume. We're given grams, and that's mass. So remember, what's our density formula? Draw our little heart. Shot to the heart, and you're to blame. You give love a bad name. Here, let's solve this problem now. So we have our problem, and we have 19.30 grams per mil is equal to our mass, 10.123 grams, over our volume. We're going to have to solve for volume. Now, we did this before where we took our volume and we multiplied it on both sides. We did that before. So let's go ahead and I'm going to show you 19. So it's volume times 19.30 grams per mil equals 10.123 grams, or 10.123 grams, yeah. But we haven't solved for volume yet. So now we need to get volume by itself. Well, right here, we're multiplying by 19.30 grams per mil. So now, to get volume by itself, we're going to divide by 19.30 grams per mil. And that's going to cancel that out on this side. Here, we have to do the same thing. If you scratch the left, you have to scratch the right. So we divide it by 19.30 grams over mils. And you notice that our grams, because we have grams on top and grams on bottom, they'll cancel out. So our volume is going to equal 10.123 divided by 19.30. Our volume is going to be equal to 0.524 milliliters. Almost finished. All we're doing is practice problems. How many meters is 25,000 centimeters? Well, we're looking for meters. We're given 25,000 centimeters. We always start with what we're given. Put what we want on top, which is meters. This is perfect practice. All these practice questions are perfect practice for your quiz. Once centimeters canceled out, we know that there's 1 meter for every 100 centimeters. My centimeters will cancel because I have one on top, one on bottom. 25,000 times 1 divided by 100 will give me 250 meters. That is it. Take the quiz as many times as you feel you need. The highest score will be given. So it's good to do that for practice. And let me know if you have questions.